My name is Doreen, and I'm part of the CCSE group here in the CRD department. And today I'll be talking to you about a new numerical method that we have developed and implemented to more efficiently model low Mach number flows with complex chemistry in stellar applications. So in the astrophysics community, there are many interesting phenomena that occur in the low Mach number regime. Here I've listed 3 of them. And the first one is a Type 1a supernova progenitor, which Don kind of talked about earlier. And the Type 1a supernova is basically a powerful explosion that occurs in the binary system, and it tells us interesting things about the universe, such as how far its host galaxy is, and how fast the universe is accelerating. The second problem is a Type 1 X-ray burst, and these have actually been observed in real time by NASA telescopes on the International Space Station just last year, I believe. So it's something that is pretty exciting to the community. And the third one is the convective Urca processes, which can occur in both Type 1a supernova progenitors and also neutron stars. And they're largely responsible for the cooling of neutron stars. So what we're interested in our group is to develop computational tools to bridge the gap between observations and theory. So the first question we ask is why can't we just use traditional compressible methods to model low Mach number flows? And the reason for that is it's actually very expensive to use fully compressible methods. It would take a really long time to only simulate a couple of seconds of real time. And this is because the time steps are very limited due to the very high speed of sound in space. And so the timescales that we're really looking at for these types of problems are on the order of hours to days. And so this is really infeasible for using fully compressible approach. There is also high cost required to resolve the local flow in smaller spatial regions of interest. And so we want to have a special method to be able to solve low Mach number flows. And in fact, we actually have a software that already does this called Maestro. And Maestro was developed about more than 10 years ago in the same group. And in the last 2 years, we've been porting it over from Fortran to C++ using the AMRX framework. And we kind of rebranded it as Maestro X because it's built on AMRX. And in this process of porting it over, a lot of astrophysicists have been wanting to do more complicated problems with more complex chemistry. And unfortunately, the original numerical approach used in Maestro is not quite suited for flows with complex reaction networks. And so we wanted to implement a better numerical scheme to handle these new types of problems. So the reason Maestro X is able to efficiently compute low Mach number flows is twofold. The first is since we ported Maestro X over to the AMRX framework, we can just use the built-in functions to be able to apply adaptive mesh refinement. And then that way we can increase the spatial resolution of our solution. So for example, if we want to model a Type 1a supernova progenitor, what we would do is to increase the resolution near the center of the star, because that's where we want to determine local hotspots that will cause the point of ignition, which causes the whole star to blow up. And the second reason is that Maestro X uses a special low Mach number formulation to remove any dependence, of acoustic waves in the governing equations. And this would effectively increase the time step. So now I'm going to go into a bit more depth on this low Mach number formulation, and then we'll discuss how Maestro X solves these equations and what we did to improve its capabilities when dealing with more complex chemistry. So the first thing we want to know with the low Mach number regime is that the Mach number here is very small, on the order of 10 to the negative 2. And so this means that the acoustic waves carry very little energy, and so would not really affect the solution. And so the strategy here is to remove the acoustic waves from the governing equations, yet retain all of the remaining physics. And we do this by simply decomposing the pressure into an average base state P naught that's determined by through hydrostatic equilibrium with the average base state rho, the density. And then we also have a perturbational pressure, pi, where pi over p naught is on the order of Mach number squared. And so after we substitute this approximation into our governing equations, what we get is an improved time step that's only dependent on the velocity and is about a factor of 1 over m larger than the compressible time step. So in practice, removing the acoustic waves allows for approximately 70 times larger time steps for Maestro X. So here are the low Mach number equations. What we have here are basically just the mass, momentum, and energy equations, but with the low Mach number approximation substituted in. And then we also have this divergence constraint in purple, where it's derived from differentiating the equation of state along particle paths. And so we can see here that there's kind of 4 different numerics at play here. I want to draw attention to mainly the advection, the reaction physics. So advection occurs on a relatively long time scale, and reaction occurs on a very short time scale. And in order for us to take the same time step, what we do is we solve the reaction terms with a stiff ODE solver called VODE. And really what we want to do to improve this solver is to, or improve this method, is to do a better coupling between the advection terms in green and the reaction terms in red. So first I want to talk about the current approach in the original Maestro, and that's string splitting. So string splitting kind of works like operator splitting, except it's in a predictor-corrector approach. So if we can write the system of low Mach number equations as the right-hand side of that equation as a sum of the advection, diffusion, and reaction source terms. And then for operator splitting, usually you would integrate over half a time step of the reaction, and then you do a advection diffusion solve over the full time step, and then you end with another half time step of reactions. And then you do this twice in a predictor-corrector approach to improve the accuracy of the method. And what we find that is that string splitting method is quite robust and does really well for the types of problems that we wanted to solve 10 years ago. But it is inherently only second order accurate, and it can also suffer from large splitting errors. So we want to improve mainly on the splitting error portion of the method. So we propose this new approach called spectral deferred corrections. And the idea here is to take an approximate solution and then iteratively solve its correction equation to improve the overall solution. We can derive this correction equation here. And what this says is basically k is the kth iteration of this correction equation. And the terms inside the first integral gives you the error between each iteration. And the term inside the second integral gives you the residual with respect to the solution at time n. And the way we actually apply this in the Maestro X setting is that we would evaluate the first integral using a simple discretization, and then the second integral is evaluated using a high order quadrature. So as I talked about earlier, we have this basically 2 kind of steps to do the advection and then to do the reactions. So here are the correction equations for both of those steps. And the takeaway I wanted to show with this equation, it is pretty long, but basically I want to show that for the advection diffusion solve, when you're evaluating the advection source term here, you are taking in a time-lagged reaction source term. And so that's the coupling in that particular step. And then for the second step, when you're integrating the reactions using VODE, you're using these updated advection diffusion source terms. So here A is the exact same term that you had in the first step, and you're using that updated advection source term to evaluate the reaction terms. Oh, sorry. Okay, so here's kind of a side-by-side comparison of the 2 methods. So the one thing I want to point out here is that with this kind of better coupling, we're hoping to reduce the splitting error. for SDC. And also, I want to mention that SDC, in fact, can be made arbitrarily high order, theoretically, depending on how many times you cycle through this, the correction equations. And so we wanted to just start with a second order SDC method to have like a one-to-one comparison with the second order string splitting. And so we will only iterate this once. So now if we look at the computational requirements between string splitting SDC, we can see that they're actually quite similar. They both require 2 cost of vote to advance 1 plus n species of reaction equations. They both have 2 times 1 plus n species of advection-diffusion linear solves, and then we have 2 divergence constraint elliptic solves. And the computational efficiency here, really the difference between them is how much vote has to work to integrate those reaction terms. And we hope that with the better coupling, we can reduce some of those splitting errors, and so vote will work less hard. And that is the goal here. So the first the first problem we wanted to look at is modeling the convective phase of a type 1a supernova progenitor. And the goal of this particular problem is that we wanted to just compare the results between the 2 methods. And we wanted to run it for a while, all the way from the convection phase all the way to just prior ignition. And this is a relatively simple reaction network. It only has 3 species. So we expect string will do well, but we're not sure how well SDC will do. And these are just the initial conditions. The red is the temperature profile, the initial temperature profile, and the blue is the initial density profile in the radial direction. So here are some results. This is a plot of the radial velocities, I guess a profile of the radial velocities. On the left side, it's an animation of the red is the outwards radial velocity and the blue is the inwards. And then on the right side, we have the maximum Mach number with respect to time. And this is just to check its long time convection behavior. And as you can see, the 2 methods are pretty similar. We generally look at the Mach number because we want to see if we're still within the low Mach number regime that our approximation should hold for. So once it starts getting out of that regime, we know that we can no longer use this method. This is the temperature solutions. And again, you can see on the right side that for the maximum temperature profile over time, the SDC and strain are quite similar. So what about computational efficiency, which is what we're really trying to accomplish here with this new method? And we can look at that by doing a Nonaka plot. And so here, I'll explain what this plot is. On the x-axis is time, and on the y is the mass fraction of carbon. And this is, I plotted 1 time step here. And then each data point represents a right-hand side evaluation by vote. And so this means that the more points you have, the more evaluations you have with vote. And so vote is actually working harder to get to the solution. And the purple here is SDC, and the green is strain. So this discontinuity in the strain solution is actually caused by changes due to the advection step. So if you remember earlier when I said that strain, you take half a step of reactions, and you take a full step of advection, and then another half step of reactions, that's where this discontinuity comes from. And so if you look at this result, you can see actually that SDC isn't doing as well as strain. And we think that this is because this is a relatively simple reaction network. It's not very stiff. And so it's possible that strain's just doing a better job. But I would like to point out that if you look kind of at the slope of these individual segments for strain, they're actually evolving in the opposite direction of where they should be. And so I feel like that could mean that there is a splitting error there that could potentially get larger if you have a more complex network. So now we want to move on to a little bit more complex complex problem with a more species in the reaction network. And to do this, we model a plane parallel layer of a massive star. So I guess Don erased it, but basically you're just taking a layer of that star. And and kind of stepping it through time and see what happens. And this uses a more complex reaction network of 20 species now. And so if you look at the Nonaka plot here, I'm plotting 3 time steps. And you can see that SDC does in fact perform much better than Strang. And so we're hopeful that with more complex reaction networks, our new method does work well. So the kind of future direction that we're going in is we want to do a full spherical massive star problem. And this is to find the conditions prior to core collapse, which is what scientists are really interested in simulating this problem. And then the second thing is we would like to look at possible high order SDC methods. Like I said earlier, basically that's dependent on how many times you kind of iterate through these correction equations. And it would be nice to have an option to gain high order accuracy. And that's it for my talk. I'd like to acknowledge the Maestro X development team with Andy and Don in the group here at LBNL, and then also our collaborators at Stony Brook University, Alice and Mike. And that's it. Thank you. Any questions? Yep.
So you mentioned that for the small reaction network, you don't have a gain in terms of how much load is working, but you hope that you have a gain in terms of how much you reduce your splitting error. Did you?
Yes.
It's fine. You have a hope. Did you try to set up a case in which you could check that you reduce your splitting error, like you obtain really to a second order?
Like a very simple problem,
yeah,
right,
exactly.
that you can run. I don't think we've tried that yet.
Because
but it's definitely something that we can do.
Yeah, that's what Andy did for the convolution part, like 10 years ago.
Yeah. I don't know if we actually have a suitable astrophysics problem. That's the thing. So, but we could maybe come up with something to show that.
Yeah, because conditions can be quite different from convolutions, like in terms of velocity range, and so maybe something different.
True.
Any other questions?
All right. Thank you.